Okay, there's quite a few things to keep in mind as we're working with variables, so let's go through and review what we talked about. The first thing that we talked about is the three different ways to declare variables. So we saw that we could declare a variable and then initialize it later. We saw that we can declare it and initialize it at the same time. And then we also saw that we can use this colon equals syntax as a shorthand version of declaring and initializing a variable, and then we let the compiler decide what type to assign to that. Now normally you're going to use this third version. The only time you're really going to use the second version is when the compiler is going to guess wrong. And then the first version is sometimes useful if you need to declare the variable in a different scope than you're actually going to initialize it. We then talked about how we can't redeclare a variable, so within the same scope, we can't initialize that variable twice, but we can continue to reassign values to it, but we can shadow them. So if we declare a variable in a package scope, for example, we can redeclare that in a function scope, and that's going to shadow the variable at the higher level scope. All variables must be used in a Go application. So if you declare a local variable and that variable isn't used in the scope that it's declared or one of its inner scopes, then that's going to trigger a compiler error and you're going to have to go back and clean that up before your application is going to run. And again, the reason that that's really nice is as code evolves and it continues to be refactored and improved over time and features get retired, you don't have all these old variables hanging around and requiring allocations of memory when they're not being used for anything anymore. We also talked about the visibility rules. The first thing that you need to know is when you're working with package level variables, a lowercase first letter means that it's scoped to the package, which means all of the source files that are in the same package have access to that variable. If you have an uppercase first letter, then it's going to be exported globally, and so anything can work with that variable at that point. There is no private scope, so you can't scope a variable to the source code itself. However, you can scope a variable to a block by declaring it within the block instead of declaring it at the package level. We also talked about the naming conventions, and there are really two naming conventions that are used. Pascal case, which basically means you uppercase the first letter, and camel case. So when you're naming variables, you don't want to separate the words in the variables with underscores. You don't want to have them all in lowercase. You don't want to do anything like that. Just use standard Pascal or camel casing rules. The only exception to that is if you're working with acronyms, all of the letters in the acronym should be uppercase. The names of the variables should be as short as you reasonably can get them. So if you've got a very short lifespan of the variable, say for example a counter in a for loop, then having a one-letter variable name is perfectly acceptable. However, if you've got a variable that's got a longer lifespan, say for example it's used in a fairly long function, or if it's exported from the package, then having a longer, more descriptive variable name is certainly something that you should consider. However, please don't go crazy. Keep those names as brief and concise as possible. And the last thing we talked about are the type conversions, and how these work a little bit differently than other languages. In a lot of other languages, you would have to put the type in parens and then what you want to convert. In Go, it acts more like a function. If we want to convert an integer to a floating point 32 number, then we use float32 as a function and we pass the integer into it, and it's going to do the type conversion for us. We also learned that Go does not do implicit type conversion. So if you try and take a floating point number and assign it to an integer, Go's going to throw a compile time error for that, and that's because of the possibility of losing information through that conversion. So every time you're going to do a type conversion that might lose information, you're going to have to do that yourself so that you're making the decision, and then you can write whatever tests are required in order to make sure that information isn't lost. The final thing that we learn is when we're working with strings, then type conversions can start to get a little bit weird. So in order to handle the conversion between integers and strings and other data types and strings, we can use that string conversion package that offers a series of functions that make sure that the conversions happen the way that we expect them to. In today's video, we covered a lot of ground in this video, and I understand that it might take a little bit of time to process this and really understand all the different options that you have for primitive data types in Go. Now, before we get into the summary, I do want to let you know that a lot of times the default data types that you're given are going to be perfectly fine. So if you're working with Booleans, you're going to get a Boolean type. If you're working with integers, you're going to get that signed integer type. Floating point is going to give you floating point 64, and so on. So you don't have to memorize every single data type. If you need a specific data type, then you can certainly refer to the Go documentation in order to find out what's available for you. So let's go through and review what we talked about. The first thing that we talked about was the Boolean type of data. We found out that it can take two values, true or false, and it's not an alias for other types. So in some languages, a Boolean is actually an alias for an integer, so you might use like -1 for true and 0 for false. When Go, Boolean is its own type, so you can't convert back and forth between integers and things like that. You're going to have to work with Booleans as their own type. We also talked about the zero value for a Boolean is the value false. And so if you initialize a Boolean and don't set a value for it, it's going to receive the value false. Then we talked about the numeric types. And the first type that we talked about were the integer types. And that broke down into two different types. We have the signed integers, and there are two classes, I guess you could say, within the signed integer type. There's the int type, which has varying size, but a minimum of 32 bits, and this is going to be the most common type of integer you're going to deal with in your applications. But if you need a little bit more granularity or a little bit more resolution or control over how much memory is assigned to the integer, then you can go all the way from int 8, which is an 8-bit integer, all the way up to a 64-bit integer. We also have the unsigned integers, so where the signed integers have a plus or minus, and so they can't store numbers quite so large because they have to store a plus or minus bit. The unsigned integers can store larger numbers, but they can only ever be positive. And we have all the way through an 8-bit, which we can use the byte or the uint8 type for, all the way through 32-bit unsigned integers with the uint32. We have various arithmetic operations that we can perform on both integer types, so we can do addition, subtraction, multiplication, division, and that remainder operation. So remember, division with integers is going to give you an integer result, so you're going to lose that remainder portion. So if you need that, you can use that remainder operator to get it. We also have the bitwise operators, so we can do and, or, exclusive or, and the and not operations. And the zero value for any integer type is going to be the literal value 0. So when you initialize an integer type and don't assign a value to it, that's going to be equivalent to the value 0. You're not just going to get whatever was in memory when that variable was initialized. And you cannot mix types in the same family. Now this is going to be true throughout all of the numeric types. If you have a uint16, for example, and a uint32, you cannot add those together. You're going to get a compile time error. The next numeric type that we talked about were the floating point numbers. So they follow the IEEE 754 standard. The 0 value is similar to the integer types, the value 0. And we have two different versions. We've got 32-bit versions and 64-bit versions that we can work with. And we have several different literal styles that we can use to initialize them. So we can use a pure decimal like 3.14. We can use exponential notation, for example, 13e18 or 2e10. And it doesn't matter if that e is upper or lowercase. Or you can do mixed. So for example, 13.7e12 is a perfectly acceptable way to initialize that. We do have addition, subtraction, multiplication, and division that we can do with floating point numbers. Now, we don't have the remainder operation, but the division operation is going to give us a true floating point result, so we're not going to lose our decimal portion. The final numeric type that we talked about were the complex numbers. The 0 value of a complex number is 0 plus 0i, and they come in 64 and 128-bit versions. And the reason for that is the two components, the real and the imaginary component, are either going to be floating point 32s or floating point 64. So when you add those together, that's where you get the 64 and 128-bit versions. We have some built-in functions that we can work with. So we can use the complex function in order to create a complex number. We can use the real function in order to get the real component, and we can use the imag function in order to get the imaginary component of a complex number. Now what the data type that comes out of that depends on the size of the complex number going in. So complex 64 is going to give you a float 32 out from the real and the imag function, and a complex 128 is going to give you a float 64 out of the real and the imag function. We have the same arithmetic operations as we do for floating point numbers. We can do addition, subtraction, multiplication, and division. The final category of primitive data that we talked about were the text types. And in Go, there are really two different text types. The most common one that you're probably going to deal with are strings. Now, strings are represented as a collection of UTF-8 characters. They're immutable. You cannot change the value of a string after it's been initialized. You can concatenate strings together with the plus operator, and then you can convert them back and forth between a collection of bytes with this square bracket byte syntax and passing in the string. That'll convert it to a collection of bytes, and you can convert a collection of bytes back to a string by using the string conversion. The other type we talked about is a rune, and a rune represents any UTF-32 character. Now, runes are a little bit more complicated to work with because of the multi-step process that it takes in order to encode a character into the UTF-32 character set. So when we're working with runes as a primitive type, really all we're working with is an alias for an integer 32. Today I want to talk about constants. Constants are another one of those foundational elements that's going to be a part of almost every application you're going to write. Now, the first thing that we learned about with constants is that they're immutable, but they can be shadowed. So we can create a constant, we cannot assign a new value to it, but if we create a constant on an inner scope from an existing constant, then not only can we change the value, but we can even change the type, because that inner scope is going to shadow the outer scoped constant. They have to be replaceable by the compiler at compile time. so the value must be calculable. So we're not going to be able to access functions or command line arguments in order to determine the value of the constants in our application, but we are going to be able to do simple expressions like we talked about in the enumeration section. They're named like variables, so if you want to export the value of a constant outside of your package, then you're going to use Pascal casing, and if you want to leave it as an internal value to the package, then you're going to use camel casing to name that constant. Typed constants work just like immutable variables, so you can use them in arithmetic operations, you can pass them into functions, but they can only interoperate with the same type. Untyped constants have a little bit more flexibility, so they work just like the literals. So if you replace that constant throughout your application with the literal value of that constant, that's how it's going to work. So that's going to allow it to interoperate with similar types. So we had the value 42 defined as an untyped constant, and we could add that to an integer 16, we could add that to an integer, we can add that to a uint 16, any of those would work because the literal 42 will work in all of those cases. Then we talked about the enumeration types that we can work with, and we learned about the special symbol iota that allows us to start with the value 0 and increments one time every time we use it inside the same const block. Now the one thing that we have to watch out for is that constant values that match the 0 values of variables can cause subtle bugs in your application because you might have logic that you expect to initialize the value of the constant, and if something happens and that initialization doesn't occur, then you're going to be working with the 0 value, which might give you a false match to a constant that you're evaluating against. Using that iota operator, we can actually create what are called enumeration expressions. So we can define the value of the constant dynamically by combining iota with any arithmetic, bitwise operation, or bit shifting operation that's allowable with the primitive type that the constant is representing. I want to talk about the first. Arrays and slices are very common in Go applications, and I think you're going to see them all over the place as you start to work more and more with the language. So I hope that this conversation has really helped you understand what arrays and slices are and some basics about how you can work with them. We started our discussion by talking about arrays, and we learned how they're collections of items with the same type. So you can't create an array that has strings and integers and things like that. All of the types have to be the same, but it does collect them all together, and as we start to get into conversations about looping and things like that, we're going to find how we get some very powerful tools that we can work with when we're basing our data on arrays and slices. They are fixed size, so when you create an array, you have to specify at compile time how big that array is, and it can never change. So you can't make them smaller and you can't make them larger. There are 3 different ways that we can declare an array. We can do the literal style like you see on this first line, where we're going to specify the number of elements, and then we use a literal that's going to initialize those elements. However, we do have a shorthand notation that uses 3 dots instead of that first size, and that's going to be a little bit more robust in your application design, because if you run into a situation where you need to add another literal, you don't have to remember to update the size of the array. It's going to update automatically. We also have this third syntax where we can declare a zeroed out array. In this case, we're going to declare an array of 3 integers. Each one of those integers is going to start with the value 0. We also talked about how arrays are zero-based. So we're going to be counting from the head of the array. So the first element in the array has the index 0, the second element has the index 1, and so on. So in this example, if we ask for the index 1 of array A, we're going to get the value 3 out. We have the len function that's going to return the size of the array in case you need to know that some other place in your application, and you want to have a way to be able to handle that robustly that's not relying on the fact that you know at design time how big that array is. You can use the len function to interrogate the size of the array. Anytime you're moving the array around, it's going to copy the underlying data. So if you have a 3-element array and you assign that to another variable, all 3 elements are going to be copied to a new location in memory, and you're going to be working with an independent copy. So that can cause some unexpected behaviors, because if you change that copied array and you expect the changes to be reflected back in the initial array, that won't happen. And it can be very expensive because all that memory has to be allocated a second time. Then we moved on to discuss slices and how they're very similar to arrays. As a matter of fact, they're backed by an array. So every slice that you see under the covers, Go has an array that's holding all of that data for you. There are several creation styles. We saw that we can create a slice by slicing an existing array or another slice. We have the literal style that we can use, which is very similar to the array literal, except for we just leave those 3 dots out because the size of the slice is dynamic, and so it can be determined at runtime. We also saw how we can use the make function. So if we pass 2 arguments to the make function, the first is going to be the type of slice that we want to create. So in this example, we're going to create a slice of integers, and the second parameter is going to determine the length and the initial capacity of the slice. If we need a capacity that's different than the initial length, then we can pass a third parameter into the make function, and that's going to allow us to specify a capacity independent of that initial length. The len function returns the length of the slice itself, whereas the capacity function returns the length of the underlying array. So if, for some example, you want to control the resizing of the slice, you can go ahead and do that, and use that capacity function to understand when you're starting to get to your limits. You can also use the append function to add an element to the slice. Now what that's going to do is it's going to take in a parent slice, and it's going to take in one or more elements to add to that slice. Now through the course of that append operation, you can add elements that exceed the capacity of the underlying array. If that happens, then you are going to trigger a copy operation, and all of those elements are going to have to be copied to a new location. So be aware of that. If you're dealing with large slices of data and you end up resizing a lot of times, your application performance can suffer. You might want to think about using that 3-parameter make function in order to set the capacity of the slice close to where you need it to be. When you're passing slices around in your application, keep in mind that assigning a new value to an existing slice actually points to the same underlying array. So if you manipulate the slice in one location, it's actually going to affect all the other slices that are pointing to that same underlying data. So we talked about an example where we created a slice and removed the middle element out of it, and we saw how that actually affected the initial slice and could cause some behavior that we weren't expecting. I want to complete the video. We talked about the 2 remaining collection types that are available in Go. We talked about maps and we talked about structs. Now when we talked about maps, we learned that they are collections of value types that can be accessed by keys. They can be created as literals or via the make function, and members are accessed via the square bracket key syntax. We can check for the presence of an element within a map using this OK syntax. So we can ask for the value, add a OK, and what the map is going to return is the value type as well as a Boolean that's going to indicate if the value was found or not. Now if the value wasn't found, your value variable is going to be the 0 value of the value type in that map. So for example, if you've got a map of strings to strings and the element isn't found, you're going to get an empty string returned out. If you've got a map of strings to integers, for example, you're going to get the value 0. If you have multiple assignments to the same map, they all point to the same underlying data. So they're what are called reference types, which means that if you manipulate the data in a map in one location, any other variables that are pointing to that same map are going to see that change as well. We then went on to talk about the struct type and how they're a collection of disparate data types. So whereas arrays and slices and maps are all collecting the same data type together, a struct is unique in that it collects any type of data together. So you've got a common field name, but those fields can point to any valid data structure within Go. They're keyed by name fields, which generally follow the syntax of any valid variable, including whether they're exported or not. So if you capitalize the name of a field, then that's going to be exported from the package. If you leave it lowercase, then that's going to be kept internal to the package. They're normally created as types, but we can create anonymous structs if we need to. And again, common use cases for this are very short-lived structs, such as generating a JSON response to a web service call that's only used one time. Structs are value types. So if I assign a variable to an existing struct, then all of the struct's values are going to be copied over to create a brand new struct. So if I manipulate a struct in one location, it's not going to affect any other variables in your application. We don't have an inheritance system within Go, but we can use composition using what's called embedding. So when we want to embed one struct within another, we just list the type of the struct and we don't give it a field name. Go is then going to automatically interpret that for us and delegate any calls for fields or methods in the containing struct down to the embedded struct if that top level struct doesn't contain a member with that name. We also learned a little bit about tags and how they can be added to struct fields to describe that field in some way. So there's a lot of different use cases for this. The JSON package uses this to provide ways to map field names from Go field names, which are typically uppercase, to follow JSON conventions, which are typically lowercase. We also saw that we can use this, for example, to pass information into a validation framework, and that framework could generate errors if we need fields to be required or have rules about their length or things like that. I want to start a discussion. In this video, we started our discussion about the different control flow tools that we have available to use in our Go applications. And we started out by talking about the very basic if statements and how we can use a Boolean variable to determine if a block of statements will execute or not. We then talked about the initializer syntax and how that allows us to execute a statement that's going to set up variables that we can use to run our test against, as well as use within the statements of our if tests. We then talked about the comparison operators, and we talked about how there are 6 of them. We've got less than, greater than, less than or equal to, and greater than or equal to work with primarily the numeric types, as well as the double equals operator and the not equals operator that are available to be used more generally. We talked about the logical operators, the AND operator, the OR operator, and the NOT operator that allow us to chain together Boolean operations, as well as reverse the result of a Boolean operation in the case of that NOT operator. We talked about short-circuiting and how when you're chaining together tests with an OR operation, for example, if any one of those logical tests evaluates to true, then the remaining tests are not executed. So any side effects or any functional operations that might occur with those are not going to be executed. Similarly, with an AND test, the first part of an AND test to return a false result is going to halt the execution of that AND test. So any side effects you might be relying on afterward are not going to occur. We then talked about the 2 different variants of if tests. We talked about the if-else statement and how we can use that to execute one of 2 branches of code. So if the if test succeeds, then we're going to execute the first block of statements. Otherwise, we're going to execute the second block of statements. Related to that is the if-else if statement. And in this case, instead of determining between one of 2 paths and forcing your code to execute one of those, you can add additional logical tests. So at most, one block is going to execute. But if all of your if tests fail, then you might not get any blocks executing. And finally, I took a minute to talk about equality operations, especially when working with floating point numbers, and how equality and floats don't really get along that well. So if you do need to do some kind of an equality operation with floating point numbers, then you're going to want to turn that into some kind of a comparison operation against an error function. So for example, we were checking to see if 2 floats were equal. Instead of checking to see if they're actually equal, we divided them, subtracted 1 from that result, and checked that against an error parameter. So we decided if they were within 0.1%, they were going to be considered the same. You can use a similar type of error function with your operations, but in general, you should not test to see if 2 floating point numbers are equivalent to one another. We then moved on to talk about switch statements and the various ways that we can use those in our applications. We started by talking about how to switch on a tag, where a tag is just another name for a variable, but that variable has a special significance in a switch statement because all of your test cases are going to be compared back to that tag. We talked about how with Go we can have multiple tests with our case statements, and by doing that we can actually eliminate a lot of situations in other languages where we need to fall through and chain multiple cases together. Well, in Go, we can just add those multiple tests in the same case and eliminate the need to do that falling through. We also do have initializers available with switch statements, but instead of the initializer generally generating a Boolean, as we do with an if statement, the initializer is going to generate the tag that's going to be used for the comparisons in our cases. We talked about switches with no tags and how it adds a lot of flexibility to the switch statement, but it is a little bit more verbose syntax. So instead of the cases being compared for equivalency with the tag, we're going to actually put in the comparison operation ourselves, so we can use more than just equivalency testing. We can check less than or equal to or any other comparison function, including chaining comparisons together by using logical operators. We talk about how we have the fall through keyword available in switches and how that replaces the break keyword in many languages. So where many languages have implicit fall through and explicit breaking, in Go we flip it around. So we have implicit breaks, but if you do need one case to fall through to the next, then you can use this fall through keyword. Now, one thing to keep in mind when you're doing that is when you're falling through, any additional case logic is not executed. The fall through will override any case logic that you have, and so the next statements will execute regardless of if that case would normally pass or not. We also talked about type switches and how we can use that special syntax by adding a dot paren type paren on an empty interface in order to get the underlying type of that empty interface. So for example, if we've got an empty interface that's holding an integer, then we can use that syntax in order to get that underlying integer value. Then in our switches, we can switch against those types, and then we can make a decision based on the data that we got in. And finally, we talked about breaking out early. When we've passed into a case in our switch statement, there are times when in the middle of the case we need to exit out early because we've done some additional analysis and we've decided that we should not proceed executing this case. So for example, we've got a switch statement, and inside of that case, we're doing some validation on the data before we save it to the database. We might decide that data is invalid and we should not proceed to save it to the database. So in that case, you can use the break keyword, break out of the case, and continue execution after the switch statement. I want to continue our discussion. In this video, we talked about the second major control flow construct that we have in the Go language, the looping construct. And we talked about how we're going to use the for statement for all of the loops that we need to do in Go. So we don't have to remember a do keyword and a while keyword and a for keyword. When we use the for keyword, that's going to allow us to loop over every collection that we have. We started by talking about simple loops and how there are three basic forms for the simple loop. We've got this first syntax, which is the most basic. That's the initializer test incrementer syntax. And we're going to use that initializer to set us up in our loop, normally by initializing a counter variable. Then we're going to follow that with our test. Our test is normally going to look at the incrementer to see if it's at a certain value that's out of range for our for loop. And then we've got an incrementer, and that incrementer's job is to move the incrementer along at every iteration of the loop in order to move to the next case that we want to loop through. Now we also learned in this first syntax, we actually can leave the first and last statements on that out, but if we're going to use any of this syntax, we have to leave the semicolons in place. So leaving a semicolon out confuses the compiler. It starts to assign things to the wrong places, and so you're going to get an error in your application. So if you need an initializer or an incrementer, then you're going to have to use this full syntax. Now the second syntax eliminates the need for the initializer and the incrementer, and it assumes that the test conditions are being managed somewhere else. So in this construct, you only have the for test, and as soon as that test is false, you're going to exit the loop. The last construct that we have is the for loop on its own, and that will run indefinitely until somewhere within your for loop, the break statement is called. That leads us to how we can exit early from a for loop, and we have three concepts that we talked about with that. We've got the break keyword that will break out of the immediate loop that's executing and continue the application execution after that loop. The continue statement is similar to the break statement, except for it doesn't break out of the loop, it just breaks out of the current iteration, goes back to the incrementer, and continues execution of the for loop at the next increment. Now we can also use labels in our application and combine those with break statements in order to break out of an inner loop, and that's typically how they're used in Go. So for example, if you have a nested loop where you're iterating over two collections and you need to break out of the outer loop, then you need to set up a label and then follow the break keyword with the name of that label so that Go knows where to break out to. And finally, we talked about how to loop over collections and how the collections that we have available, there's quite a few. We've got arrays, slices, maps, strings, and channels that we can loop over, but they all have this similar syntax. We're going to use that for keyword. We're going to get a key and a value, and then we're going to set that equal to the range keyword followed by the collection that we're looping over. So the keys when working with arrays, slices, and strings are going to be the index within that collection, so you're going to have that zero-based index. With maps, we're going to get the key from that map. And the values are what you expect them to be. They're the value for that current index. Now when we're talking about channels, it's going to follow very similar syntax, but channels have a little bit of a special interpretation for these, and we'll talk about those in a future module. I'd like to finish our discussion. In this video, we talked about the final two control flow concepts that we have to be aware of in Go programming. Now, one could argue that defers and panics aren't really control flow constructs because they're not the traditional branching or looping logic that we consider, but they definitely do alter the flow of execution of our program, and so I'm going to lump them together in this category. The first thing that we talked about was the use of the defer function in order to delay the execution of a statement until the end of a function. Now these are useful to group open and close functions together. So if your open function is going to open up a resource and you need to make sure that you close that, then you can defer the call to close that resource to make sure that you're freeing up the memory and not holding onto that resource any longer than you need to. The one thing I would warn you though is be careful in loops. If you're opening and closing a bunch of resources inside of a loop, then you probably want to explicitly handle that close without the deferred keyword, because when you're using the deferred keyword, all of those resources are going to stay open until the function finishes execution, and that can cause you some memory issues, especially if you're dealing with a very large number of resources. Now, if you've got multiple deferred statements inside of a function, then they run in LIFO order, or last in, first out. So the last deferred statement that you call is going to be the first one that actually executes. And again, this makes sense because if you're opening a bunch of resources and those resources are dependent upon one another, then you're going to close them in the reverse order that you open them, which is typically the right way to go. Arguments in a deferred call are evaluated at the time the defer is executed, not at the time the called function is executed. Now that's important to keep in mind because you could pass in variables into a deferred function call, and it can be a little bit confusing if you change the value of those variables further on and those aren't reflected in your deferred statement. So just keep in mind, when you call defer, the value of those variables are going to be captured at the time that that defer is executed, not at the time the function actually executes. Now, something unplanned happens in our application, then we've got two ways that a Go application can go. It can return an error value, which is the normal case, or it can panic. Now, what you generally want to do is you want to return an error value because in Go programming, we typically don't consider a lot of things that go wrong in an application to be exceptional events or to be events that should cause the application to shut down, for example. A classic example of that is making an HTTP request and you make the request and you don't get a response from that server. Well, that's something that happens all the time. No response is a valid response. It just happens to be an error because you're looking for that resource and you got a 404 return back. So in that case, you're going to return an error value. You're not going to panic the application. Panics are used when an application gets into a state that it cannot recover from. For example, if you hand the runtime a divide by zero problem, there's no way for Go to figure out how to divide a number by zero, and so it has no way to manage that. And that's a situation where the application is going to panic. So just to summarize that, they occur when an application can't continue at all. Don't use them when a file can't be opened, unless it's a critical file. For example, if you're opening a template that's used in a web application to generate your view layer, then that might be something that's worth panicking over. But if you're trying to open up a log file and you can't get there, well, there's no reason to panic for that necessarily. You just need to return an error value and then inform somebody that the logs aren't available. Now, a situation where you might want to panic is unrecoverable events. So if you're starting up a web server and it can't get a hold of the TCP port that it's supposed to be listening on, then that's probably a situation where a panic makes sense. The function will stop executing immediately at the point of the panic, but deferred functions will still fire. If nothing handles that panic, then eventually the panic is going to go up the call stack, it's going to hit the Go runtime. The Go runtime has no built-in handling for panicking situations, and so the program will then exit. If you do have a panicking situation that you feel that you can recover from, then you can recover using the built-in recover function. Now that function is used to recover from panics. It's only useful inside of deferred functions, and the reason for that is because of the behavior of panic. Remember, when an application starts to panic, it no longer executes the rest of that function, but it will execute deferred functions. So the proper place to use the recover keyword is inside of a deferred function that's going to look for a panicking situation, and if the application is panicking, then it can go ahead and decide what to do with it. The current function will not attempt to continue, but if you do recover, then higher functions in the call stack will continue as if nothing went wrong. Now, if that's not the behavior that you want, if you call that recover function, you look at the error that's returned from the recover function and you can't handle it, remember that you can go ahead and rethrow that panic by calling the panic function again, and then the panic will continue to propagate up the call stack. I want to talk about pointers. In this video, we talked about pointers and how to use them in the Go language. Now, we haven't seen a lot of practical application for pointers yet, but we need to understand what pointers are before we get into that. So over the next couple of videos, we'll get into why you would want to use pointers and the benefits of them, but for now, we're just trying to introduce the basic subject. So we started by learning how to create pointers, and we learned that if we prefix a type with an asterisk, that's actually going to declare that type to be a pointer to that underlying data type. So for example, we have this asterisk int, which is going to be a pointer to an integer. We also learned how we can create pointers using the address of operator to get the address of an existing variable in memory. Then we learned about dereferencing pointers and how we can use that asterisk operator again, but this time in front of a pointer instead of in front of a type, and use that to drill through the pointer to get at the value that the pointer is pointing to. We also learned that when you're working with complex types, such as pointers to structs, those pointers are automatically going to be dereferenced for us, so our syntax doesn't get cluttered up by a whole bunch of dereference operations and parentheses. Then we moved on to learn how to create pointers to objects, and we learned that there's a couple of different ways. So the first thing that we could do is use that address of operator to get access to a pointer to an object that we've already created. So in this example, we've got an instance of a myStruct object called ms, and then we can use that address of operator to create a pointer p to that struct. But we can also do that directly. So if we precede an object initializer with that address of operator, then we can actually directly create a pointer, and we don't have to have an intermediate variable that's holding that value. We can also use the new keyword to initialize an object, but we can't initialize the fields at the same time. So the behavior is a little bit different because we're going to have to use the new keyword that's going to zero out all the fields in a struct, for example, and then we're going to have to come in later and initialize all the values. The last thing that we talked about was types with internal pointers. And we saw how, while they're treated exactly as any other variable type when we do an assignment, their behavior is a little bit different. So all assignment operations in Go are copy operations. So whenever you have a variable A and you create a variable B and set it equal to A, all of the data in A is going to be copied in order to create B. However, slices and maps contain internal pointers, and so even though they're copying pointers, and so they're pointing to the same underlying data. We're going to take a deep dive. In this video, we talked about functions and how to use them in the Go language. And we started out by talking about the basic syntax of a function. And we saw that this is about as simple of a function as we can get. So we start with the func keyword. We have a name for that function. And again, if that first letter is uppercase, then that function is going to be published and allowed to be executed from outside of the package. But with a lowercase first letter, it's going to be kept internal to the package. Then we follow with a matched set of parentheses. And then we have an open and closed curly brace. Now the open curly brace has to be on the same line as the func keyword, and the closed curly brace has to be on its own line after the final statement of the function. Then we moved on to talk about parameters, and parameters allow us to pass data into the function to influence how that function executes, basically providing some variables for the function that are passed in from the outside. So we talked about how parameters are passed in as a common delimited list of the name of the parameter and the type of the parameter. So we see here we're passing into the foo function two parameters, the bar parameter that's of type string and the baz parameter that's of type integer. Parameters of the same type can be comma delimited and the type can be listed at the end there. So in this case we're passing in bar and baz as parameters, and both of those are going to be of type integer. When pointers are passed in, the function can change the value in the caller. So by default, we're going to be passing in the values themselves, and so the Go runtime is going to be copying that data and passing it into the function, so any changes that are made inside of the function aren't going to be reflected in the caller scope. However, if you pass in a pointer, then you are going to be able to manipulate the value inside of your function, and that will have an effect in the calling scope. So the only exception to this rule is when you're working with slices and maps. Since they work with internal pointers, any changes inside of the function to the underlying data is always going to be reflected inside of the calling scope. We also talked about how you can use variadic parameters to send a list of the same types in. So it must be the last parameter in the parameter list. It's received inside of the function as a slice. And you see an example of the syntax right here. So we've got the function foo. It has one parameter bar that's of type string, and then a parameter baz that's a variadic parameter of integers. So inside of this foo function, we're going to have a slice called baz, and that's going to contain all of the integers that have been passed in. Once your function finishes doing its work, a lot of times we want it to return a value back out. And in order to get that information back out, we're going to use return values. So if you have a single return value, all you need to do is list the type. So in this case, our foo function needs to return an integer. We can also specify multiple return values. So if we're going to do that, we need to put parens around the types that we're going to be returning. So in this example, we're going to be returning an integer and an error. And this is a very common pattern that you're going to see in Go applications, where we're going to have our functions return the intended value and then an error value that's going to let the caller know if anything went wrong. That way, the function itself doesn't have to determine whether the application needs to panic or execution can't continue. It just knows it wasn't able to do what it was asked to do, and then it can delegate what that error means to the application to the calling function. You can also use named return values. So when you do that, instead of just providing the types in the return list, you're going to provide the name of that return value. So when you do that, the runtime is going to initialize that value for you to the zero value for that variable. And when you use the return keyword, all you need to do is enter return on its own. Go is going to find the current value of those return variables, and that's what's going to be returned out of your function. Another special behavior of Go is you can actually return the addresses of local variables as return values, and those are going to be treated properly. So when you do that, those variables are automatically promoted from local memory or stack memory up into shared memory or heap memory, so you don't have to worry about those values being cleared out as the function's stack memory is reclaimed. We then started talking about anonymous functions, and we talked about a couple of different uses for those. So we have this immediately invoked function, which really isn't used too often in the Go language, but it's as simple of an anonymous function as I could get. The only potential advantage that you have here is that you can create an inner scope, so local variables that are created inside of this anonymous function aren't going to be available outside, but I haven't seen that very often. It's not going to be very often that you're going to need to use this kind of a function. Then we also talked about how we can take that anonymous function and actually assign that to a variable. So in this example, we've got the variable a assigned to the value of that function. And then we can invoke the a function just like any other function. The only difference between this and the normal declaration of a function is that the a function can only be invoked after it's been declared. So when you declare a function using the traditional syntax, it's actually declared at the time that the package is initialized, and so it's always available to you. When you're using this syntax, you have to make sure that a is initialized before you can call it. Extending on that discussion about the ability to assign functions to variables, functions are types just like any other type in the Go language. Anytime you can use a primitive or a slice or an array or a map, you can use a function. So you can assign them to variables, you can use them as arguments, they can even be return values from functions. Then we also talked about how, since a function is a type, we have to have the ability to create a type signature. So if you're declaring anonymous functions, it's often most convenient just to use that := syntax and declare your anonymous function, and the type is going to be inferred. However, if you're using a function as a parameter to another function, or as a return value from a function, then you're going to need to specify that type signature. So we see an example here. In this case, we've got the definition of a function f, and that function is going to take 3 parameters, 2 strings and an integer, and then it's going to return an integer and an error type. So it's basically the same as when you're declaring a function normally. The only difference is we don't have the names for those variables, because those names will be provided when we actually implement the function. We just need to know the types that are coming in and the types that are coming out at this point. The last thing we talked about were methods, and how a method is a special type of function that executes in the context of a type. Now, a type doesn't have to be a struct, although that definitely is a very common use case for methods. You can actually attach a method to any custom type. So you can create a type of an integer, and then you can add methods onto that integer. When we create a method, we're going to use a modified version of the basic function syntax. So before the name of the function and after the func keyword, we're going to provide another set of parens. We're going to provide a local name for the type that's going to receive that method, and then we're going to follow that with that method type. Now that variable is what's called the receiver for the method. So in this case, our G variable is what's called a value receiver, which means we're going to get a copy of that greeter object, and that's going to be passed into the greet method. However, we can also use what are called pointer receivers. So by adding an asterisk in front of that greeter type, the method is going to change. So instead of passing a copy of the greeter, we're going to get a pointer to the greeter object in there, and then any manipulations we make to the greeter object in the greet method are going to be reflected throughout your application. Now that's very powerful if you need the method to be able to manipulate the state of the object. It's also much more efficient if you're dealing with large structures, because instead of copying the entire structure, it only has to copy a pointer, and that's normally a much more efficient operation. I want to talk about one of the cool. In this video, we've talked about interfaces and how to use them in the Go language. We started with a discussion of the basics of interfaces, so how to create them and how to implement them. And we ended up with code that looks something like this. So we're defining an interface as a type. So we're going to start with the type keyword, the name of the interface, and then the keyword interface. And then inside of curly braces, things are going to be a little bit different than if we were defining a struct, for example. If we were defining a struct, we would put data fields inside of the curly braces because we're defining the data that that structure is holding. With interfaces, we're defining behaviors, however. So instead of adding data fields, we're going to add method signatures. So we see here in this example, we're going to define a write method that accepts a slice of bytes and returns an integer and an error. And then we implement that interface by creating a method on our type that has the same signature. So we don't have to explicitly state that we're implementing the interface. We implement the interface by implementing the interface, by having the methods there that match the type signature for the interface's methods. Then we talked about how to compose interfaces together, and how this is a preferable approach versus creating a single monolithic interface. If you can, break that interface down into smaller types and then compose them together. And we did that something like this. So we're going to create multiple interfaces. So we have a writer interface and a closer interface. And then when we compose them together, just like when we compose structs by embedding, we can embed interfaces into one another. So we can create a writer-closer interface that embeds the writer interface and the closer interface. So to implement that writer-closer interface, you have to implement the write method, because that's defined by the writer interface, and you have to implement the close method as it's defined by the closer interface. So by doing this, you can actually pass smaller chunks of your interface around your application. So for example, if a method only needs a writer, it doesn't need a closer, then you can actually pass this writer closer as a writer and it'll work just fine, versus passing the entire writer closer along and potentially exposing methods to the consumer that aren't really necessary. Then we talked about type conversion and how we can drill through the interface to get at the underlying types in case we need to work with those directly. So we had an example here where we created a writer closer instance and the underlying type was a pointer to a buffered writer closer, and how we could cast that back to a pointer to a buffered writer closer by using this syntax here where we have a dot after the object and then inside of parens we put the type that we want to cast to. Now we learned that when we did this, if the type assertion failed, then we're actually going to panic our application. So remember to use that comma OK syntax if you want to get a Boolean variable out that you can run tests against to see if that type conversion succeeded. And then we talked about the empty interface and type switches. The empty interface is nothing magic. It's just an interface defined on the fly that has no methods on it. Now it's special in that every type in Go implements the empty interface. So you can store anything you want in a variable of type empty interface. And then very often we're going to pair that with what's called a type switch. And we see an example of that here, where we're going to use the switch keyword, we're going to have the object, and then dot and parens like we do with the type assertion. But instead of having a concrete type that we're asserting against, we put the keyword type in there. And then in our case statements, we're actually going to put in the data type that we're asserting against. So in this case, we're looking for integers or strings, or we have a default case in case the value stored in I is neither an integer nor a string. After that, we talked about implementing with values versus pointers. And we learned about a concept called method sets. Now, when you're working with types directly, you never have to think about this because the methods are always all of the methods assigned to that type. But with interfaces, the rules change a little bit. The method set of a value is all of the methods with value receivers. So if you're going to try and implement an interface with a value type, then all of the methods that implement that interface have to have value receivers. With pointers, things are a little bit more flexible. Because pointers always have access to the underlying type as well, the method sets for a pointer is all of the methods regardless of the receiver type. So all of the value receivers as well as all of the pointer receivers. So pointer types are definitely more flexible when you're implementing interfaces. Just keep in mind, you don't want to assign pointer receivers everywhere without thinking about the idea that that gives access to the underlying data of that type, and so that can allow methods to alter that underlying data even if you don't want them to. So be careful when you make that choice about using pointer receivers or value receivers. The last thing that we talked about were some best practices that have evolved over the last few years about using interfaces in the Go language. And we talked about use many smaller interfaces whenever possible, and then if you need larger interfaces, go ahead and compose those together with interface composition. Don't export interfaces for types that will be consumed. So if you're creating a library and somebody else is going to be consuming a type, go ahead and publish that concrete type out there. Don't create an interface assuming you know how people are going to use it. Allow them to create the interfaces that your type will implement. That way they don't have to implement a whole bunch of methods in their test suite that they never even use. Do export interfaces for types that you will be consuming, however. So again, these 2 points are exactly opposite of how you're going to think about interfaces if you're coming from another language such as C# or Java that have explicit implementation of interfaces. So when you're defining a type that you're going to be consuming in your package, then go ahead and export interfaces. That way whoever's using your package can create their own concrete types and implement the interfaces that you need, so you don't need to worry about the implementation. You just need to worry about the behaviors that they're exposing to you. And then, if possible, define your functions and methods to receive interfaces. Don't get too crazy with this, so don't go over the top. Use common sense with this. But if you have the option of receiving interfaces, for example, if you don't need access to the underlying data, then go ahead and define an interface that you're going to be receiving. That way, it makes your methods and functions more flexible, since you can have multiple implementations that you never thought about at design time, and your functions and methods will continue to work even when those new concepts are thrown at your application. I want to have a conversation. In this video, we learned about Go routines and how we can use them to create concurrent and parallel execution paths in our applications. We started by learning how to create Go routines themselves. And we learned that by adding the Go keyword in front of a function call, we've created a Go routine, and that's all that it takes. There's no special semantics, there's no special things that need to be done. It's simply a function call with the keyword Go in front of it. Now, when we're using anonymous functions, we in general want to pass data as local variables. So you want to add a parameter into that anonymous function and pass data into the Go routine instead of relying on the closures to prevent any kind of race conditions as you try and manipulate that data. Now, that's not always true. We saw with weight groups that we access that globally because that was our intention. We truly did want that to be available in multiple scopes. But even then, we could pass a pointer in order to be very clear about what information that Go routine should have access to. Then we talked about the different ways that we can synchronize multiple Go routines together. One of the challenges that we have with Go routines is now we've got all sorts of things happening, and there's no way to ensure without synchronization how they're going to interact with one another. Now, for a lot of concurrent calculations, that's not a problem at all because the two might not be related to one another. But often you get into situations where you're relying on the result of multiple calculations, or something needs to know the result of the work that's been done, or you've got a shared memory issue and you need to make sure that those Go routines aren't trying to manipulate the same data at the same time. So we can use wait groups to wait for groups of Go routines to complete. So we saw that we have three methods that are interesting there. We have the add method to inform the wait group that there are more Go routines for it to wait on. We have the wait method that's going to block the Go routine that it's called on until the wait group is completed. And then we have the done method available on that wait group that lets the wait group know that one of the Go routines is completed with its work. We also talked about the mutex and the RW mutex and how those are generally used to protect data. So if you have a piece of data that's going to be accessed in multiple locations in your application, then you can protect that access by using a mutex or an RW mutex to ensure that only one Go routine is manipulating that data at one time. We then talked about parallelism and how parallelism can introduce some really tricky challenges into your Go applications. We talked about how by default Go will use the number of CPU threads equal to the number of available cores on the computer that it's running on. We talked about how we can change that by using the Go max prox function from the runtime package. And we talked about how more threads will generally increase performance, but too many can actually slow it down. So in general, if you're developing an application, you want to start from day one with Go max prox greater than 1 to find any concurrency and any race conditions early on in your application development. But don't settle on a final number until right as you get close to production and you have a performance test suite that you can work with to find out what the best value for Go max prox is for your application. Because while the starting number is a very good number to start with, a lot of applications actually perform better with a value higher or lower than that default value. And finally, we wrapped up with a discussion of some best practices to keep in mind when you're working with Go routines. We learned that if you're a library developer, you should avoid the creation of Go routines that are going to be exposed to the consumer of your library. Let the consumer control the concurrency of your application because they're the ones that are in the best place to know if something needs to be executed single-threaded or if it can be executed concurrently. When creating a Go routine, know how it's going to end. It's very easy to get into situations where Go routines start leaking memory because they're never cleaned up because they never quite get done with their work. Now, normally a Go routine is killed as soon as it finishes its execution. And we saw that with the main function. The main function runs in a Go routine, and that Go routine terminates as soon as the main function exits. We also saw in our say hello function, as soon as it printed its message out and the function exited, that Go routine was killed and it was cleaned up. So it was very clear when those Go routines' life cycle was going to be over. However, if you've got Go routines that are listening for messages in a continuous loop, then make sure that you code in a way to shut those Go routines down so that once you're done using them and clean up the memory that they're using. Also, as you're going along with your application development, check for race conditions. It's not that hard to do. You just have to add -race onto the Go command that's compiling your application, and then the Go compiler is going to analyze your application and try and locate places in it that have the potential of accessing the same memory at the same time or in an unsynchronized way, causing very subtle and potentially very disastrous bugs for your application when it gets to production. Over the course of in this video, we talked about channels and how we can use them to synchronize data transmission between Go routines. We started out by talking about the basics of working with channels. And we learned that we can make our channels using the built-in make function and how that's really the only way that we have available in the Go routine to make a channel. When we do make those channels are strongly typed. So we're going to use the chan keyword to indicate that we wish to create a channel, and then we have to follow that with a data type that the channel is going to be able to send and receive. Now that data type can be anything. It can be a primitive like we see here with an integer, it can be a struct, it can be an interface, but it does have to be strongly typed. We can send a message into the channel using this arrow syntax, and the position of the arrow kind of indicates the direction that the data is going to flow. So in this case, we list the channel, we have the arrow, and then the value that we wish to send into the channel. So notice that the arrow is pointing into the channel. But when we want to receive messages from the channel, then the arrow is leading out of the channel. And so we're going to use the same arrow syntax, but the channel is going to be added after the arrow instead of before. And we can have multiple senders and receivers. As a matter of fact, it's very common for one channel to be distributed among multiple Go routines, and that way you can have multiple data generators that are sending messages into the channel, as well as multiple data receivers, and that allows you to balance the performance between senders and receivers. So if you can generate data 10 times as fast as you can process it, then you can create 10 times as many receivers, and that way you can balance the workload out between senders and receivers. We then talked about how to restrict data flow. By default, channels are bidirectional constructs, so you can send and receive data into a channel. Now, very often what we want, though, is our Go routines to be designed to handle channel data only in one direction. So we saw that we can do that by passing in the channel, but then on the receiving side, so for example in the argument list of the function, we can actually specify the direction that we can work with by, again, adding that arrow, and we either add it before or after the chan keyword, depending on what kind of channel that we want to make. We can make a send-only channel by putting the arrow after the chan keyword, and we can make a receive-only channel by adding the arrow before it. We then talked about buffered channels, and how buffered channels contain internal data stores that allow us to get around this limitation of channels. That by default, a channel will block the sender side until a receiver is available, and the receiver side will be blocked until a message is available to come out of the channel. So you can actually block a Go routine on the sending side or the receiving side of the channel. So if there's no position available in the channel to add the message, then the sending side will be blocked until a space does become available, and if there's no message in the channel, then the receiving side is going to be blocked until a message becomes available for it to work with. So in order to decouple that, we can add an integer as a second argument to the make function, and that's going to allow the channel to have an internal buffer to decouple your senders and receivers, just in case there are situations where data is generated faster than it's received. So just like it says here, we want to use buffered channels when sending and receiving have asymmetric loading. So if we can generate messages faster than we can receive them, then a lot of times a buffered channel is a really good way to go. We then moved on to talk about for range loops, and specifically how to work with them with channels. And we learned that they basically work the same way, but there are a couple of subtle differences. The first thing is, the first parameter that you're going to receive from the for range loop when working with channels is the value itself, not the index like we saw when we were using for range loops over arrays, slices, and maps. And we saw how we could use for range loops to monitor a channel and process messages as they arrive. So the for range loop is just going to keep pulling messages as they come in off the channel, and it'll process them as they come. Then when the channel gets closed, the for range loop is going to detect that, and it will go ahead and exit the loop. And finally, we talked about select statements, and how they work kind of like switch statements, but they work only in the context of channels, and how they allow a Go routine to monitor several channels at the same time. Now, if they block if all channels are blocked, so if there's no messages available on any channel, then the select statement will block by default. And then when a message comes in, it will go ahead and process that on the proper case. If multiple channels receive a value simultaneously, then the behavior is actually undefined. So because of the highly parallel nature of many Go applications, you can get into situations where messages arrive on two channels at virtually the same time. So one of those cases will get the nod from the select block, but you can't be sure of which one's going to get it. So there is no rule like in switch blocks where the first one that matches is going to get it. It could be anyone. So the ordering of the cases in your select statements really doesn't matter from the standpoint of how those conflicts are going to get resolved. Now, if you do want a non-blocking select statement, remember that you can add that default case in there. So if there are no messages on any of the monitored channels, then the default case will go ahead and fire, and so the select statement will process and execution of the Go routine will continue from there. Okay, so that wraps up what I have to talk about with channels, and really it brings us to the end of the discussion that I have for this Introduction to Go series. For now, this is Mike Vansickle wishing you luck in all of your Gopher endeavors. Take care.